Welcome back to Physics 151. You should remember that we've already talked about several special thermodynamic processes. For example, we've talked about an isobaric process, where the volume changes but the pressure stays constant. Then we've also talked about isothermal processes, where the pressure and volume both change, but they change in the way that keeps the temperature constant. And then the third special process that we talked about was isochoric or isovolumetric, where the pressure changes but the volume remains constant. There's one other kind of special process that's often discussed in the context of thermodynamics, and we're going to talk about that today and work through a special formula that gives the relation between the pressure and the volume when this kind of process happens. And it's called an adiabatic process. And what adiabatic means, it's really just a special word that talks about a kind of a process where heat is neither absorbed nor released from a particular system. And therefore Q, the term in the first law of thermodynamics, is equal to zero. There's two ways that this can happen in practice. We can approximate this kind of a process either by having a process happen so rapidly that there's not much time for heat to escape, or to have the system that we're talking about be so well insulated thermally from its environment that heat can't get in or out. And either way, this process is adiabatic. And during an adiabatic expansion, which is the example that we're going to consider here, the pressure and volume both change, but in a different way than they do for an isothermal expansion. And so first, let's think qualitatively about what happens. This is the kind of question that you might get on a quiz sometime. So for an adiabatic expansion, let's ask what happens to the temperature. And how can we figure that out? Well, first of all, if the process is an expansion, V increases. And from the definition of the work done by the system, if the volume increases, the system is doing work, so work is positive. Since it's adiabatic, by definition, Q is equal to zero, and therefore the first law, which tells us that delta U is Q minus W, well, if Q is equal to zero, then delta U is equal to minus W. W is positive, so delta U is less than zero. The internal energy goes down. We know that the internal energy is proportional to temperature for an ideal gas, therefore delta U is proportional to delta T. And if delta U is less than zero, delta T is less than zero, and that means the temperature goes down. And that's what makes an adiabatic expansion different from an isothermal expansion. And now let's illustrate this on a PV diagram. So the gas beginning at an initial pressure and volume P1V1 expands to P2V2, where V2 is higher than V1, and of course P2 is going to be less than P1, but it goes to a lower temperature. And so we can illustrate this on a PV diagram by using two isotherms. The two dotted lines here that are curved represent two isotherms. The top one represents an isotherm at temperature T1. The bottom one represents an isotherm at a lower temperature T2. And so an adiabatic expansion starts at P1V1 in our example. The expansion means it goes to a higher volume and therefore a lower pressure, but in the process of the expansion, the temperature goes down. If this, by contrast, had been an isothermal expansion, then the entire process would happen along the top isotherm. The temperature would stay constant. But in this case, the temperature goes down, and so the process takes us from one isotherm down to another isotherm, and therefore the temperature goes down. This kind of a curve for an adiabatic process is called an adiabat, in the same way that for an isothermal process, the curve is called an isotherm. Now let's consider mathematically what happens during this process. So delta U is equal to delta Q, or Q minus W, and therefore if we consider very small changes for a general process, according to the first law of thermodynamics, a small change in its internal energy should be equal to the tiny amount of heat absorbed minus the tiny amount of work done, right? For an adiabatic process, therefore, this is minus dW, and since dW is equal to pdV, according to the definition of work, then du is simply equal to minus pdV, all right? And for a monatomic gas, We'll use that as a specific case, and then we'll show how this can be generalized to other kinds of gases later. But for a monatomic gas, we remember that U is equal to 3/2 nRT, so a differential change du is 3/2 nR dt. And now du we know is negative pdV. So we've got this expression here. There's a relationship between the change in temperature and the change in volume for this kind of process. We'll come back to this in just a moment. So let's apply the ideal gas law to describe an infinitesimal step for an ideal gas when it changes from one pressure and volume to another pressure and volume. And so we start with the ideal gas law. PV is equal to nRT, and mathematically we take what's called a differential of both sides of the equation. And when you take the differential of the product of two variables that are each changing, something like the product rule applies. So we write this as PdV plus VdP. And that just tells us that a change in the product PV can happen either through a small change in the volume or through a small change in the pressure, or both, right? And so that's what's happening here, is both of these are potential changes. And on the right-hand side, the n and the r are constants. T is the only variable, so we have nr dt. And that's what we get when we take the differential of both sides of this. Now, we remember from the previous slide that du is 3/2 nr dt, and that's equal to minus pdV. Well, look at the right-hand side of the equation on top. We have nr dt, and that's the same thing that we have multiplying the 3/2. So let's take the left-hand side of the top equation and substitute it in on the left-hand side of the bottom equation. And therefore it becomes 3/2 times the quantity pdV plus VdP equals negative pdV. We've just made a substitution. Notice that there's a pdV on both sides of the equation. So let's go ahead and multiply both sides by 2/3 and then combine the pdV terms, and what we're going to get when we rearrange this is that pdV is equal to minus 3/5 VdP. So I've skipped a couple of steps algebraically, but that's what the result turns out to be. Now, what good is this? Well, when you see an equation like this, where there are changes in two different variables involved, it's a very simple form of a differential equation. And in order to solve this one, what we're going to do is employ a technique called separation of variables. And we used this earlier in the course in a different context. So what we want to do is get all the p terms on one side of the equation and all the v terms on the other side of the equation. So when we do that, we just basically divide both sides by p and divide both sides by v, and then multiply by 5/3. So we get dp over p equals minus 5/3 dv over v. All right. Now what can we do with this equation? We take this equation and integrate both sides of it. So what we're doing is we're saying this is a process that starts at p1 and v1, and then as the expansion takes place, we end up at a final pressure P2 and V2. And so the equation that we had that we're integrating now tells us how small changes in P are related to small changes in V. So if you take a look at both sides of this equation, of course the negative 5/3 comes outside the integral on the right, and we've basically got the same kind of integral. It's going to give us a natural log. So on the left-hand side, we'll get the natural log of P evaluated between P1 and P2, and that's simply the log of P2 minus the log of P1, which can also be expressed log of the ratio P2 over P1. That's what the left-hand side reduces to. On the right-hand side, we get minus 5/3 log of V2 minus log of V1, and another way to write that is the log of the quotient, V2 over V1, right? And then we're going to simplify this right-hand side in two separate steps. First, we remember that when you have a constant multiplied by a natural log, it's the same as the natural log of the argument raised to the power of that constant. So this is the same as natural log of V2 over V1 to the negative 5/3 power. The negative 5/3 simply ends up in the exponent. And we can also get rid of the minus sign there, which is a little bit inconvenient, by just remembering that V2 over V1 is the same as V1 over V2 to the negative 1 power. And so employing that relationship, now we get log of P2 over P1 is log of V1 over V2 to the 5/3 power. And then, doing just a little bit more algebra, we have the natural log of two quantities, and if the natural log of two quantities are equal to each other, then the quantities themselves must be equal to each other. So P2 over P1 is V1 over V2 to the 5/3. And then we're going to get the quantities that have the 2 subscript on one side of the equation and the quantities with the 1 subscript on the other side, and we get the final equation for a monatomic ideal gas that's undergoing an adiabatic process. And you'll notice that this is different than what we would have for an isothermal process. For an isothermal process, you can show from the ideal gas law that you would simply have P2V2 equals P1V1. Here, we've got this 5/3 power, which makes it a different form of a relation, and therefore adiabatic curves are different than isothermal curves. Now, remember, we developed this equation for the special case of a monatomic ideal gas, and so what if we're dealing with diatomic gases or polyatomic gases? Well, we can immediately generalize this equation, and you'll remember that we had this constant gamma that was introduced a little bit earlier, and it had different values for monatomic and diatomic gases, and you can even tabulate what gamma is for different kinds of polyatomic gases that don't quite fit the diatomic relationship. And so we can write this as P2V2 to the gamma equals P1V1 to the gamma power, where gamma for a monatomic system is 5/3, which is what we had in the box up above. And for a diatomic gas, gamma is 7/5. And you can look up in the table in your textbook values for gamma for other kinds of more complicated gases that have more than just a single or 2 atoms. And so gamma then can be determined from experiment and can be used in this kind of a relationship to describe the behavior of gases in adiabatic processes. So that's where I want to stop for now. Just remember, going back a couple of slides, remember the graph that showed this process. And so what we've done is we've developed an equation. If we know the initial pressure and the initial volume for an adiabatic process, and let's say we know one of either the final pressure or the final volume, we can use that equation to figure out the unknown. And so if we know 3 of the 4 values of P1, P2, V1, or V2, we can figure out the 4th one from the information that's provided. So it's another special kind of thermodynamic process. It's useful because in the real world there are processes that behave at least approximately like this. Remember, they either occur so fast that heat has no time to be exchanged, or very little heat does, or they're occurring for systems that are so well insulated that very little heat can get in or out. So it's a useful approximation, and we will often describe the behavior of systems that have adiabatic processes. I will see you in class.